Hello and welcome to iitiansgateclasses once again. So we are continuing with the AVL tree. So we have seen that the insertion and deletion, insertion basically in the AVL tree. Similarly, we will see also deletion in the AVL tree. So we have seen that in insertion, the balancing may take place at several places. And to balance a tree after insertion, right? After insertion, what will happen? Like to find out the position of insertion, like in binary search tree also we have seen that it could be skewed, but AVL tree is balanced. Okay, so to find out the position of the insertion where we have to insert the node, it will take order of log n. Okay, so this is the time complexity to insert a single node in AVL tree. Okay, so this is the time complexity to insert a single node in AVL tree. Not ALL, AVL tree. Okay, and AVL tree are height balanced, and we know the balancing factor, right? That is 0, -1 or 1. This could be the valid balancing factor. Okay, now if we want to create an AVL tree, we have to insert n nodes in the tree. Okay, initially the tree is empty, then we insert one node, then another node. Similarly, if we insert n nodes, so to create given n nodes, we have to create a AVL tree from those given n nodes. And insertion of each node is taking basically log n. So it's order of n log n. Okay, approximately. It's basically less than n log n because initially the tree is empty. Okay, you can consider it like this, that if we insert n by 2 nodes, suppose we have inserted n by 2 nodes. Okay, already n by 2 nodes are already in the tree. N by 2 nodes are already in the tree, and we have taken some time complexity here to insert n by 2 nodes. Now the tree has some n by 2 nodes. Okay, now to insert further n by 2 nodes, it will take n by 2 log n by 2 order of. So this is basically nothing but order of n log n. Okay, so this is how, like, this is very simple interpretation. This is not the correct one, but this is how you can remember it. Now let's see an example where we basically delete few nodes from the tree. Suppose initially a tree would look like this: 100, 50, 120, 110, 150, 160, 10, 70, and here it's 80, 5, 30, 20, and 40. Now it's asked to delete 110. This is the task to given. So AVL tree deletion operation is not only about to delete a node, it's also about balancing the tree again, right? So let's delete this node and try to create the same tree again. So once we delete this node, okay, our tree will look like this: 100, 50, 120, 150, 10, okay, 10, 70, 80, 5, 30, 20, and 40. Now, once you check that it's only imbalanced at this node. Okay, it's only imbalanced at this node. It's LL problem here. Everywhere else it's balanced. So let me try to write the balancing factor also. Here the balancing factor 0, 0. For leaf node it's 0, right? Here it's left minus right, so it's -1 here, -2 here. It's not LL, it's RR actually. RR. Okay. RR. Here the balancing factor is -1. Here the balancing factor is -1. Here the balancing factor is -1. So 1, 2. So it's not -1, it's +1 actually. Okay. Here the balancing factor is it's 1, 2, 1, 2. Is it okay? Sorry. The height of right subtree here is 1, 2, right? 2. Height of right subtree. Height of left subtree is 1, 2. Okay. Here it's 0. Here it's 0. 1, 2, and 1, 2, 3. Sorry. It's not 0. It's actually +1. +1. Okay. The left height is 3. The right height is 2 only. So that is why it's +1. Now here 1, 2, 3, 4, and 1, 2, 3. So it's +1 here also. Looking at this the whole tree balancing factor, by looking at the balancing factor, we can simply say that it's imbalanced at this node. Okay, imbalanced at this node. So we have to apply for RR problem. We have to do left rotation. So once you do the left rotation, our tree will look like this. It will look like this: 150 here, 120 here, and 160 here. Now again, let's try to draw the balancing factor. It's 0, 0, and 0 here, and +2 here. See, the height of left subtree here is 4. Okay, 1, 2, 3, and 4. Height of left subtree is 4. Height of right subtree is maximum height of right subtree is height is actually the maximum depth. So it's actually 2. That is why it's +2. Now what is the problem here? It's actually LL problem here. LL problem here. Right. So we need to address the LL problem. Why LL problem? Because if it's +2 here, it means that we are getting this +2 from this direction, from this node and this node, from this edge and this edge. See, I am highlighting the edges. From these two edges, we are getting the height. If we have got the height, the maximum height, or you can say the maximum depth from this edge, then we would have considered this edge, but that's not the case here. Okay, so that is why, let me use red color to highlight. That is why this is one edge and this is another edge. So it's LL problem, LL problem. Now how to solve LL problem? Using right rotation. Now if you remember the right rotation we have done using the subtree. Here let me rename the subtree again. Let me rename the subtree again. This we will consider as A. This we will consider as B. This we will consider as C. And this we will consider as D. Now let's write the whole tree again. It's basically 100 here, 50 here, 10 here. Okay, so this is the tree. Then we have A here, B here, C here, and D here. That is the case. Once in LL problem, we do the right rotation. In LL problem, once we do the right rotation, our tree will look like this. Okay, after right rotation, our tree will look like this. 50, 10, 100. Here we have C. Okay, let me use red color for subtrees. Here we will have C. Here we will have D, A, and B will remain at the same position. Okay, so using this, try to pause the video, and because I already circled the subtrees like A, B, C, D, using this this tree as a reference, keep it handy. I'm drawing the whole tree again. Okay, I'm drawing the whole tree once more. I am replacing this ABCD again with these ABCD actual values. Okay, so our tree will look like this. 50 here, 100 here, 70 here, 80 here, 150 here, 120 here, 160, and here we have 10, 5, 30, 20, 40. So once you delete a node, in insertion generally, or tree insertion deletion, generally we have to do several readjustment, okay, several readjustment. So for each readjustment or for each rebalancing, it will take order of one time only, that's it, right? We are just linking 2-3 nodes only. We are just linking 2-3 subtrees, just changing those links. If you remember, these links are nothing but in a structure, these links are nothing but left and right pointers. I explained it earlier. Okay, these are nothing but left and right pointers. Okay, so if you see, check again that this 5 is the left subtree, which is A, 30, 20, 40 is B. Okay, 5 is A, 30, 20, 40 is B, 70, 80 is C, and this whole thing is D. Okay, you can check and verify. Right, so this is how you can basically rename the subtrees, and once you delete the node, you can rebalance them. Okay, so this is the case. Now let's move on to the next question, where in this tree only we want to delete 70. So once we delete internal node in binary search tree, we have seen that we will replace it with either predecessor or successor. Here, the predecessor is nothing here, but we know the successor. The successor is 80. How do we calculate the successor? We move right one time to go to the right child node, then move to the leftmost node. Now here, in this subtree 70-80, once we move the right side, there is nothing to go left. So the 80 is in order successor. It's in order successor. Try to write down the whole tree, or in order will look like this: 5, 10, 20, 30, 40, 50, and 70, 80, 100, and so on. So you can see the in order successor is 80 here, right? It's 80. So we'll replace 70 with 80. Let's simply erase this thing now, and we replace it with 80. Now, is there anything which got imbalanced? There is nothing which got imbalanced. Okay. See, again, let's try to calculate the balancing factor. It's 0 here, 0 here, 0 here, 0 here, 0 here, 0 here. It's 0 here. It's -1 here, 0 here, -1 here. Here the height is 1, 2, 3. It's 1, 2, 3. So it's 0 here. So it's between -1, 0, and +1. So we don't have to do any rebalancing. That's it. Now let's try to delete one more node. Let's delete something like Let's delete 80 now. Not 80. Let's delete 150 now. 150. So once we delete 150, 150 can be replaced by 120 or 160. Suppose we delete it, we replace it with 150, 120, right? In order predecessor. So the in order predecessor of 150 is 120. So once we replace it with that, our tree will look like this. After deletion of 150, 120. Okay. So this is the case now. Again, the balancing factor here is it's 0 here, -1 here, -1 here, 0 here. Okay. Again, let's delete something else. Like if we delete 80, you will face the same problem as the previous one. So this is your assignment. You can pause the video and try to delete 80 from here. Draw the balancing factor. Try to find out the problem where imbalancing is happening. So right now this factor is it's -2 here, so it's LL problem. So to sort LL, we will right rotate it. So after right rotation, it will look like this. After right rotation, it will look like this. 120, 100, 160. So now what are the balancing factors? Our balancing factors are 0 here, 0 here, 0 here. Here the height is 1, 2. Here the height is 1, 2, and 3. So it's +1 here. Right? Nothing to worry about. So this is how you can see the balancing factor. Wherever the imbalancing happens, for example, if here imbalancing happens, I will see the problem from which edge I am getting the height. Okay, here I am getting the height from here. So I can say that, okay, if imbalancing happens, for example, if it's -2 here, -2 here, there's nothing here. For example, if there's nothing here, okay, I can see that it is basically LL problem. I can make it LR also, like LR also, no issue. But if I try to configure LL problem, I try to solve LL problem, that would be far easier. So this is how you can solve the problems. Let's see one more problem which are in alphabets. Okay, so somebody can give you, instead of number, they can give you alphabets also. So in alphabets, you can consider that the left one is basically the smaller alphabets and right one are bigger alphabets. Okay, so in alphabetical order, you can consider like this: K, B here, okay, A here, E, and D here, I here, and here I have something like N. Now these alphabets are like A is the smallest one, M is the biggest one. Okay, so on the B you can see the A falls on the left side, E falls on the right side, D falls on the left side, and I falls on the right side. Okay, now if somebody asks you to delete something, like if they ask you to delete M, you delete M, then you see that, okay, from where am I getting the problem? Let's draw the balancing factor after deletion of M. Okay, so our balancing factor here is 0, 0, 0, 0, -1. Okay, here +2. It's actually not only +2, it's actually +3. 1, 2, 3, +3. So it was actually imbalanced previously also, which cannot happen. So you can reconsider the tree, that our tree is actually M here and V here. Now we have deleted the V. After deletion of V, what is the rebalancing factor? It's 0 here. Here the height is 3. It is 1 here, so it's plus 2. So now the problem is LR. It's LR problem. Okay. So in case of LR, what we do first? We do left rotation first. We do left rotation first. Okay. So let's do the left rotation first. Here we do left rotation first. We try to adjust this tree first in LR. On the right side, we do the left rotation. So this subtree will look like this now. E, B, and here I will have on the B we have A here. Okay, and here I will have B. Here I will have I. After left rotation, my tree will look like this subtree, and this is connected to K only, and I mean here. So I have done the left rotation on this part, on this subtree here, right? So my tree will look like this. You can check the reference if you don't know how we solve the LR problem. I have given several examples. Now, once the LR is done, now the problem will look like RR problem. Okay. So now if you check the problem, it will look like RR problem. And how to solve the RR problem? After left rotation, our problem will turn it into LL problem, not RR. Sorry. It's on the left side now, so it's left problem. It will look like LL. Now we do right rotation here. Okay, right rotation here. Once we do the right rotation, our tree will look like this. E, K here. We apply the right rotation here. K here, M here. And on the right side, we have I here, B here, A, and D. Now you can see the balancing factor again. So the balancing factor is 0, 0, 0, 0, 0 here, 0 here, and 0 here. It's perfectly balanced. This may not happen, but it's again a valid AVL tree. Valid AVL tree. Okay. So if you face LR problem, you will do the left rotation here to make it a LL problem. Once it becomes LL problem, you do a right rotation here. Once you do the right rotation, our tree will look like this. You can convert them into a subtrees also. Okay, you can convert them. In LL problem, we are going to consider only 3 nodes. Rest all are subtrees. In LL problem, we will consider only these 3 nodes. Rest all are subtrees. So after rotation, you can map them. Now you can see that, okay, B is smaller than E, A is smaller than B, D is greater than D, I is smaller than K, okay, M is greater than K. So this is how you can balance them out. So like this, you can practice more AVL trees, LR, LL, various rotation problems, because in many GATE examination and other PSU examination, they may ask you, they can give you a tree, or they can tell you to construct a tree. Okay, so like a single insertion, you can insert various nodes and construct the whole tree and again balance it out. So after each insertion, you have to check the balancing factor at each node and you have to balance them out. Okay, so this is how you can do your work on AVL tree. Now we will move to our other data structure like stack and. Okay, now let's see one more data structure, which is stack. Okay, so what is stack? Stack is basically last in, first out. Okay, so it is generally the operation of stacks. Operation of stacks are also called LIFO. Last in, first out. Okay. So you have seen the stack of plates in many parties at your home also. Generally, we arrange the plates like this. Okay. So when we try to put the plate, we will put the first plate after second, and first plate is at the bottom. Then we put second, third, fourth, fifth, sixth, and seventh, and eighth. Eighth plate has been put last in the stack, but whenever somebody came and try to pull out the plate, that person will pull out the topmost plate, which was inserted lastly in the stack. So that is why it's called last in, first out. So whichever has been put last will be taken outside first. Now, what all are the benefits of this thing? So generally, I have told you that in programming language, we have two kinds of spaces. One is stack. Whenever a program executes, we have two types of spaces, stack and heap. Heap is dynamic, okay? Heap is dynamic. Dynamic means whenever our program is executing and we declare some variable there, or we do some like this malloc, calloc, it will occupy space in heap area. Okay, the data structure, dynamic data structure will occupy space in heap area. And what is stack? Whenever our program is executing, it calls various functions. For example, if we define functions in functional programming, where we call functions to do our work, this function has some task assigned to it. It will do, for example, a plus b, c equal to something like this, right? But after doing this, it is basically calling another function b, where it's transferring c value. So a function, in the definition of a function, it's calling b. Till the function b is not completed, a cannot return back. And for example, there is some function, pre-function, in which we have called a. Okay. Now, till the execution of a is not done, we cannot return back pre. Pre-function definition or its variables should always remain in the execution space, right? So that is why we create a stack. So for example, if we have main function where we called pre-function, this main reference, this main return point, or you can say this main function will come at the bottom and it's not returned yet. Before returning main, we have called the pre-function. And this pre-function have called a, then a have called b. Now there could be some variables or some declaration that may happen in this stack area, okay? But those cannot be dynamic. The static declaration at the compile time, I will tell you in the programming language what is static, what is dynamic there. But whichever is static will come under this stack area. Now, once this b and itself, like for example, there is some b and we are printing C here. Once this print ended, it will return back to a. Okay, see, this a is calling b. Once it's returned back to a, this p have deallocated its memory. It's returned back to a. Now a will return back to pre. Okay, whichever function is the calling function. This is called calling function. This is called called function. So obviously the calling function will always be at lower position in stack compared to called function, because once the called function returns to the calling function, then only the calling function can return back like this. So this is the order of execution. This is how each programming language maintain the function's returns address. It's not like we are writing the function here. It's actually return address. Return address. Okay. I will tell you what return address is in the programming part. So a function A, B, C, D. The function are calling like this. So it's executing like this. First A have called B, B have called C, C have called D. Now, once the execution of D is done, it will return back to C. Execution is done, it will return back to B, then A. Okay, that is why stack is very important. In recursive calls also, sometimes you get stack overflow. Very famous stack overflow error. Because if you did something like that, okay, you have a function A in which you have called function A again without defining the if condition here or the base criteria here, without defining it here. What it will do, it will call A, then A will call A again and again. But stack have some limit, right? It has some limited memory. Once that memory have exceeded, it will give you an error, stack overflow error. In recursion, if the base criteria is not very clear, where do we have to end the last function? Okay, if it's not clear, then we face this error, stack overflow error. That is why the stack is very important. Okay, because you won't understand the programming language if you don't understand the stack. You won't understand how a computer executes its operations. For example, if you've done A plus B, okay, let me use small letters for operators. If you have done something like A plus B minus A, B, C, star D. If you have done something like this, the machine will use a stack to calculate its value. Okay, if you have done 1 plus 2 minus 3 multiplied by 2, what will be the value? Try to find out its value. Using stack, we will do such operations very easily. Okay, very easily. So this is how we can go and try to do the things. So now let's formally define a stack. What is a stack? So I have told you that a data structure is nothing but storage plus operations on that storage. So a stack is nothing but it's a data structure. Stack is a data structure that stores the data in like this vertical manner, right? Like we have seen this like 10, 20, 30, 40, or some function calls like A, B, C. And it defines some operations on this storage. The operations are push, pop, is empty. Okay, and we can have is full also. That depends upon your programming language or your convenience. So generally it's push, pop, is empty. Okay, generally we define only three these three basically operations into consideration. Is full is for like if we implement the stack, if we implement the stack using an array. Okay, so an array has a limited space or predefined space, right? Because array is always sequential in address or contiguous in address, right? If our array is like this, 1000 address here, 1002 here, 1004, 1006, 1008, something like this, right? Now, if you define like, okay, this is our array size. So you always try to fill the stack in this manner and try to empty the stack in this manner. Okay, so you can visualize this array like this, that you are filling the stack like this 1, 2, 3, 4, 5, 6, 7. So whenever you are trying to get the element, you will always get the element from top, right? I have given you the example of plates. You always get the element from the top. So this is the top here. This is the top. This is the top here. So you will get the element from here. You will make it empty. Then you will get the element here, then here, then here. So you always grow like this and you always shrink like this. Okay. So let's define the operation of stack. So let's define in programming language. Let's define what is a stack. Instead, we say that we have a pointer top. Initially, it's -1. -1 means stack is empty. Stack is empty. We have an operation push. Push. Okay. So push is basically, it's like, this is our stack. Using array, we are saying this is an array which we are using to implement the stack, and we are right now implementing a operation push. S is an array. This is the total size of the array, and then we have top, which shows what is the current location of the stack. Okay, this is the element that we want to push. X is the element that we want to push. Now, before pushing into stack, we have to check whether there is a space there. Okay, so we say that if top +1 equal n, it says that our stack is full. Okay, it says that printf stack overflow. Okay, right now we are implementing stack using an array which is called S, capital S. Okay, so we cannot do anything. Stack overflow and exit from here. If this is the full condition, top +1 equal n, right? Else stack is not full, we can insert into the stack. So we say that do top equal to top +1. Increment the top first. I have told you that our stack is basically in array implementation. Here, in array implementation, we have seen that if this is the array, or element are like this, the top will always point out to the last topmost element. So if we want to insert anything, we have to increase the top from here. Top will increase to the next position. Now here we can insert the element. Here we can insert the topmost element, or we can insert the element. So we say that S top equal to X. Okay. So this is basically, now this whole operation can also be written like this: S plus top plus top equal to X. Now what is plus top and what is top plus plus? What is plus top and what is top plus plus? So this is increment of the operation in the same line of code. This is the increment after the current line is executed. Okay. So for example, if you say that, let's say top is equal to 2 here, and print plus top. If you print plus top, it will print 3. But if you print If you print top plus plus, it will print 2 only. But after this line get executed, it will assign the value top 3. So for example, after this line, if you try to print top, right? Print top. This will give you 3. This will print 3. So the top plus plus is print the current value of top, then increase the value. And plus plus top is increase the value first, then do anything else, right? So here you have seen that we are doing plus plus top. So it is increasing the index. Initially the index is -1 because we are doing array implementation. Okay. So if you insert the first element, it will be inserted as index at index 0th index. That is why its initial value is -1. Okay. Similarly, let's do one more operation, which is pop operation. Int pop. Here the push is void actually. Why void? Because we are not returning anything. We are just inserting the value into the stack. Here we want to insert the, here we want to pop the topmost value and try to have it in our hand. Okay. After this function will return the topmost value by deleting it. That's what the pop is. Pop means if our top equal -1, it means we are underflow. We say that okay, stack underflow. Or you can print that stack is empty. Stack is empty. Okay, stack is empty. And exit from here. We cannot do the pop operation if stack is empty. Else, we will pop the element. And how can we pop the element? We say that okay, int y equal to s top element shows that the topmost element, and do top minus and return y. And you can do all these 3 lines of code into a very single line. You can do return s top minus. Now you are not doing minus top. Why? Because first you want the current element, then you want to decrease. It means you want to execute this line. After that, you want to decrease the value of top. So these 3 lines can be implemented using this simple one line. Return s top minus. Okay. Whichever suits you better, you can use any one of them. Right. So these are the operations of stack. This is how you can implement stack. Now let's see some operations like okay, so that's it for today, and we will see some more complicated stack implementation of array, where in a single array we want to use single array for multiple stack implementation like this, right? Those question can be asked, and where we want to check the efficiency of stack and the application of stack, which is very important. So the application of stack is like recursion. So recursion is not possible without stack. Okay, and infix to postfix. So what is infix? If we say 2 plus 3, this is infix. But generally, our computer don't write 2 plus 3. Computer don't understand 2 plus 3. Computer generally understands plus 2, 3. Postfix is 2, 3 plus. So it will say that okay, this is the operator, and this is binary operator. Binary operator. Okay, so it understands like this. Plus 2, 3. Postfix means you are sending the operation after operators. not in the middle of the operators. So this is operator 1, this is operator 2. So, okay, so postfix means you can write it like operator 1, operator 2, then operation. This is postfix. So this is plus, this is 3, this is 2 here. And what is infix? Infix is a simple mathematics that we calculate in our notebook or in calculator. We write it like operator 1, operation, operator 2. Okay, like 2 plus 3. Okay, but we generally, whenever we provide infix expression, it's converted into postfix, then computer calculate it. Okay, after that we will see some more stack applications. If time allows us, we will see more stack. Like one of them is the postfix evaluation. Postfix evaluation. Okay, this is also very important. So if an expression is given in postfix manner, how do you evaluate it? Okay, using stack. So without stack, you cannot evaluate postfix expressions. Thank you all for joining. I will see you in next lecture. Thank you.